Hi, welcome to my video on special theorems related to the parallelogram. And the first theorem that I'm going to look at is what we call the midline theorem. A segment formed by two midpoints of the sides of a triangle is parallel to the third side and half the length of the third side. So we're going to prove this theorem called the midline theorem. And this theorem is probably awkward to prove, because if you had to do it on your own, you probably wouldn't come up with the way to prove it. But let's have a go at it. It says that let's number or letter the triangle first. We got a triangle A, E, K. And we're going to label the midpoints as B and C. So we have a segment formed by the two midpoints. So that's BC is the segment formed by the two midpoints. And we're going to prove that BC is parallel to EK and BC is a half of EK. So we're given a triangle AEK with B and C, the midpoints of AE and AK. And we're going to prove that BC is parallel to EK and BC is a half of the length of EK. So let's do the proof. And in order to do the proof, what I'm going to do is extend BC outward. I'm going to extend BC out to the right. I'm going to extend it out so that I'm going to extend it out to F so that CF equals BC. And when I do, I'm going to join FK. So that's state number one. We're going to extend BC to F, and we're going to join FK. And also, we're going to say that we're going to extend it so that CF equals CB. And that's a construction. Now, since we did that and we made them equal, what we have is that C is the midpoint. C is the midpoint of AK, and that's given. Hence, we have AC equals KC, definition of a midpoint. And that means we have these two equal by the midpoint. We have angle 1 and angle 2. I'm going to label them here. So angle 1 is equal to angle 2 by VOAT, vertically opposite angles theorem. Two segments intersecting form vertically opposite angles formed are equal. That means we have a pair of triangles congruent. So the triangle ACB is congruent to the triangle KCF. And if we look at it closely, that's a side angle side congruency. And as a result of that, we have AB equal to KF. And the reason is C P, C, T, C. Corresponding parts of congruent triangles are congruent. And as a result, let's use the other midpoint. B is the midpoint of AE, and that's also a given. And that gives us that AB is equal to EB, definition of a midpoint. And that means that EB is equal to KF by transitive property. Transitive property, and that's in 6. Notice that AB is equal to KF, AB is equal to EB, so EB is equal to KF. That's 6 and 8. So let's put 6 and an 8 there so you can see what I'm talking about. So we had these two are equal because of the congruent triangles, and AB is equal to BE because of midpoint. Therefore, we have BE equals FK. And notice that these are the opposite sides. And notice I'm going to establish the fact that this is a parallelogram. And to do that, I'm going to say that angle A is equal to angle 3. And that's because of the congruent triangles C, P, C, T, C. The triangles are congruent, so angle A is equal to angle 3, C, P, C, T, C, and as a result, I have AE, or AB, or AE, is parallel to KF. And that's converse of the PLT. And notice that these are alternate interior angles. Alternate interior angles are equal. So that means that we have that B, F, K, E is a parallelogram. B, F, K, E is a parallelogram because we have one pair of opposite sides, parallel and equal. And they're parallel in, let's see, they're equal in right here. EB is equal to KF, and they're parallel here. So 9 and 11 are the two statements where they're equal and parallel. Remember, if AE is parallel to KF, it means that AB is parallel to KF. It means that BE is parallel to KF. So once you say any 2 points on this line, they're parallel. So the line can be named in 3 different ways. So as a result, we have BF is parallel to EK, which is what we had to. BF is parallel to EK by definition of a parallelogram. But also when we say that, so when we say BF, we're also saying that's the same as saying that BC is parallel to EK, which is what we have to prove. So because this is a parallelogram, I had to go BF is parallel to EK, which means that BC is parallel to EK. So we have the sides parallel right here. Now I need them equal. So what happens is that C right here, C is a midpoint of EK. C is the midpoint of BK, or sorry, C, or these two are equal. And I said C is a midpoint. Yes, C is a midpoint of BF. And as a result, that BC is equal to a half of BF. And since that's a midpoint, it's called a midpoint. You can say midpoint theorem or midpoint property, whatever you want. Because these are equal, because that's a midpoint, then we have BC is a half of the large one. And hence, we have, did I say that BF is equal to EK, opposite sides of a parallelogram are equal. Hence, BF is equal to EK. That means that BC is a half of EK by substitution. And the substitution occurred in 14 and 15. Let me explain. BF equals EK, so I replace BF right here with EK by substitution. So now I prove that the opposite sides are parallel, and I proved that BC through the two midpoints is parallel to EK, which is the third side, and BC is a half of EK. So the proof's done, but I had to extend this out so that these two segments are equal, and that helps me to go through the proof. Other than that, I'm not sure how you would do it. Okay, let's go through another proof. And this proof is called the midpoint of the hypotenuse of a right triangle is equal distance from all the vertices of the triangle. So what we're given a triangle, we're given a right triangle, ATK, and we're given that the angle ATK is a right angle, and the midpoint of the hypotenuse. So that means that M is the midpoint of AK. And AK, since this is the right angle at T, ATK, since this is the right angle, AK is the hypotenuse. So M is the midpoint of AK, which is the hypotenuse. So we're going to prove that MA equals MK equals MT. So M is equal distance from A, K, and T. So we're going to prove all these equal. Okay, to do the proof, again, to do this proof, I'm going to select this point right here, which I'm going to call F. I'm going to select F to be the midpoint of TK. So I'm going to let F be the midpoint of TK, and I'm going to join MF. And that's a construction. So you're allowed to pick F as the midpoint of this, and you're allowed to join these segments. And as a result, what I have is that I have M, F, parallel to AT. And we just proved the theorem. It's called a midline theorem. And what I mean by the midline theorem, have two midpoints of sides of a triangle. So this is the midpoint of AK. This is the midpoint of TK. So the segment that passes through these two midpoints is parallel to the third side, AT. So that's the midline theorem that we just proved. So let's continue. And we have the angle ATK is a right angle, and that's given. So as a result, that means that AT is perpendicular to TK. Definition of perpendicular segments or lines. And as a result, we have MF perpendicular to TK. And there's a proof that we did on incongruent triangles that said if TK is perpendicular to one of two parallel lines, then it's perpendicular to the other. So if a segment is perpendicular to one of the parallel segments, then it's perpendicular to the other segment. And we prove that in the congruent triangle unit. So we have a perpendicular. That means that we have, these are perpendicular. Let's name this 1 and 2. That means that angle 1 equals angle 2. They're perpendicular. So the reason is that perpendicular segments form congruent or equal adjacent angles. Again, that proof is done in congruent triangles. The unit on congruent triangles is extremely important to have done first, as you're seeing. So we have F is a midpoint. So that means that we said that F was the midpoint. That means that FT is equal to FK. Definition of a midpoint. And as a result, what else do we have? Let's see, I have MF equals MF. I said as a result, but not. I have this segment equals this one by midpoint. I have these two angles equal because they're adjacent angles formed by perpendicular lines. I have MF equals MF, and that's a common side to the two triangles. As a result, I have the triangles, number 9, I have the triangles congruent. So the triangle is MFT and MFK. MFT and MFK. And they're congruent by side, angle, side. Side, angle, side congruency. And hence I have MT equals MK CPCTC. CPTCT. Corresponding parts of congruent triangles congruent. These two triangles are congruent. MKT, MKF. MKT, MFT is congruent to MFK. Therefore, these two segments are equal, CPCTC. And we have M as the midpoint of AK. So I don't have that written down. So I have to say that M is the midpoint, make it of AK. It's given. It's the midpoint of the hypotenuse. So that means that MA equals MK, definition of midpoint, and hence, if you look, I have MT equal to MK, MA is equal to MK. That means I have MA equals MK equals MT, and that's transitive property. Again, more than once. And the transitive property is occurring in 11 and 12. Sorry, 10 and 12. 10 and 12 gives me all of these equal. So the midpoint of the hypotenuse of a right triangle is equal distance from all three vertices. And I had, again, do an extra on this proof by creating this midpoint here. An idea that students probably might not come up. Yeah, if you work at it long enough, you might come up with them. And another proof to do using the PLT. And using a proof, no, when I said PLT, what I mean is midline theorem. We got to be careful. So we have a triangle EGI with F, H, and A midpoints of EG, EI, and GI. So F is the midpoint of EG, H is the midpoint of EI, A is the midpoint of HI. So if I put all of them down right here, so F is midpoint of EG, and I have H, the midpoint of EI, and A is the midpoint of GI, and that's the givens. We want to prove that FHIA is a parallelogram. FHIA is a parallelogram. And in order to prove a parallelogram, I need to prove opposite sides are parallel, opposite sides equal, or one pair equal and parallel, or the diagonals bisect each other, or a pair of opposite angles equal. And one way I'm going to do it here, I have, these are midpoints. So I have F and H are midpoints of these two sides, EG and EI. So that means that FH is parallel to GI. And because these are two midpoints, F and A are midpoints of the sides of this triangle, that means that FA is parallel to EI, and that's midline theorem. So two midpoints, this FH is parallel to GI. So that means that these sides are parallel and these sides are parallel. So if FH is parallel to GI, that's the same as saying that FH is parallel to AI. And that's the same as saying that FA parallel to EI is the same parallel to HI. So therefore we have these two are parallel, these two are parallel. That means that FHIA is a parallelogram. And we could say definition of a parallelogram. Or we could say that what? Two pairs of opposite sides of a quadrilateral are parallel. So that's why we have a parallelogram by definition, or you can state that reason. And there's the proof done with these midpoints. Again, we use the midline theorem to do that proof. Okay, and we have one more, the last one to do, number 4. Hopefully everything is going well, and you can see how the midline theorem is used in the math, and that will come up again when I do coordinate geometries. It will come up again when you do other proofs. So it's good to know the midline theorem. Prove a parallelogram is formed by joining the midpoints of the sides of a quadrilateral. A parallelogram, this is a quadrilateral, 4-sided figure. So a parallelogram is formed by joining the midpoints of the sides. So let's call quadrilateral A, B, C, T. And let's let X be the midpoint of AB. Let's let Y be the midpoint of BC. And let's let W and V be the midpoints of TC and AT. And we're going to join these midpoints. There you are, we're joining them. So what I did, I took the statement and I drew the quadrilateral. I plotted the midpoints and I joined them up. So we're given that A, B, C, T is a quadrilateral. I'm just going to use QUAD, quadrilateral with, and I'm going to, instead of writing them all down, I'm going to say that X, Y, W, V are the midpoints of AB, BC, TC, and TA respectively. And what that means is that X is the midpoint of AB, Y is the midpoint of BC, W is the midpoint of TC, V is the midpoint of TA. And we're going to prove that V, X, Y, W is a parallelogram. And in order to do this proof, we need an extra segment. We need to form 2 triangles. So I'm going to join TB. That's a diagonal off the quadrilateral. And this diagonal, TB, forms 2 triangles on the inside, ATB and CTB. So these 2 triangles. So notice I have 2 midpoints here. So this line is parallel to this one, or this segment is parallel to this one. Midline theorem. We have 2 midpoints here, so this segment here is parallel to TB. And also, this segment is a half of TB by the midline. And this segment, WY, is a half of TB. So we're going to use, again, the midline theorem to do this proof. So here we go. Put it all together. So we have X, Y, W, V are, instead of writing them down individually, midpoints of AB, BC, TC, TA. And that's a given. There's a given. Number 2. Because these are midpoints, okay, now I also have to join T and B. So that join T and B is a construction. Now I can say that VX is parallel to TB. Midline theorem. And also that WV is parallel to TB by midline theorem. Because these are the 2 midpoints, then this segment is parallel to this one in this triangle, ATB. And the same here. This segment WY is parallel to TB because it's in the triangle CBT. And that means that VX is parallel to WY. We can't say transitive property or substitution if two segments parallel to the same segment, then segments are parallel. So notice TX and WY are both parallel to TB, so that means they're parallel to each other, and that proof was done on incongruent triangles. Number 5 now. So we know that TX is a half of TB. VX is a half of TB. Also, WY is a half of TB. And that's a midline theorem. Now the reason I did the parallel lines first by midline theorem to get this statement, now I did half the length by midline theorem. So that means that I have that Vx is equal to Wy. And we can have, they're both equal to a half of TB, so that's a transitive property of equality. I can say transitive here because I got equality, but I don't have equality, or parallel lines can't be done as a transversal or transitive, not transversal, transitive. And number 7, so I have TX parallel to WY. I have, sorry, I said TX again. VX is parallel to WY. VX is equal to WY. So that means that VX YW is a parallelogram, and the reason we have one pair of opposite sides parallel and equal. I also could say that that's how you prove the parallelogram, because of one, you could say properties of a parallelogram, but not, you have to have one pair of opposite sides equal and parallel. So, and that's in, they're equal in 6 and parallel in number 4. So we can say 4 and 6 are the statements where they're parallel and equal. And we have this proof down. Again, the midline theorem helped us to do these proofs. So that brings us to the end of this video on the proving the midline theorem and some examples using the midline theorem. And if you like my video, click on the like button, subscribe button, visit my math website www.mathfullyexplained.com to find more information about me, my videos, and the content that's on my YouTube channel called Math Fully Explained. Thank you for viewing my video. Bye bye.